This is the last section in Chapter 5, Polynomial and Rational Functions, and we're going to talk about complex zeros and also the fundamental theorem of algebra. So the first objective is going to be to use the conjugate pairs theorem. Then the next thing is going to be to find a polynomial function. With specified zeros, so you'll be given some zeros. And then find the complex zeros of a polynomial function. So once again, let's recall the four equivalent statements. If r is a real zero of a polynomial function, then it means r is an x-intercept of the graph of f. The point r0 is a point on the graph of f. X minus r is a factor of f. That means it divides evenly into f with no remainder. And r is a solution to the equation f of x equals 0. In other words, r is a root of the equation. So you'll hear the words root, intercept, solution, zeros used kind of interchangeably, but in different contexts. So far we've been looking only at real zeros of polynomials. And when you're factoring a polynomial over the real numbers, the sum of squares is prime. So over the real numbers, remember that x squared plus 1 is prime, or x squared plus 9, or x squared plus 4, any sum of squares. So a lot of people really want to factor those over the real numbers, but they can't be factored over the real numbers. Okay, so now let's talk about a variable in the complex number system, and it's referred to as a complex variable. And a complex polynomial function f looks just like the ones we've been looking at. The difference now is that the coefficients could be complex numbers. There's no requirement that they be real numbers. The a sub n has to not equal 0, or your degree is lower. And then n is a non-negative integer. So remember, the powers have to be integers and positive. And x is a complex variable. So as before, we call the a sub n the leading coefficients, the one that's in the front when we write them in order by degree decreasing. And a complex number r is called a complex zero of f if it's true that f of r equals 0. So keep reminding yourself that f of r equals 0 means r is a 0 of f, and x minus r is a factor of f. So in college algebra, we will be only using coefficients that are real numbers, but I wanted to introduce the idea that it's possible that you can have complex numbers as the coefficients. So we, though, will allow the variable x to be a complex number, but the coefficients will be real. So that will simplify life a little bit. When you're factoring a polynomial over the complex numbers, the sum of squares can be factored. So x squared plus 1 equals x plus I, x minus I, because if you FOIL that back together, you'll see you get plus ix minus I squared. So these will cancel. But I squared is -1, so minus a -1 comes out to x squared plus 1. So when we're allowing complex numbers into the game, then the sum of squares can be factored. So all these ones we did before, like x squared plus 4, you get x plus 2i and x minus 2i, and it can be factored. So in the real number system, there are polynomial functions with no real zeros. So this would be one that's an example. F of x equals x squared plus 4 has no real zeros. So in contrast, in the complex number system, every polynomial function has as many zeros as its degree, as long as you take multiplicity into account. So every quadratic function has degree 2. There will be always 2 solutions as long as we allow complex numbers. So there's a famous mathematician, Carl Gauss, and you hear his name come up again when you study magnetism. Gauss is one of the units that you use studying magnetism. When he was 22 years old only, he proved this theorem, which has come to be known as the fundamental theorem of algebra. It says every complex polynomial function, f, of degree n greater than or equal to 1 has at least one complex zero. And if you think about this, you can remember that complex numbers include all of the real numbers. So if we draw the picture of the complex numbers, all the real numbers are inside here. So really what it's saying is for every complex polynomial function, as soon as you allow complex numbers for solutions, we'll have at least one complex zero, which is pretty amazing when you think about it. So that theorem's not that useful in and of itself, but it's useful because it can be used to prove this theorem, which is very useful to us. So every complex polynomial function with a degree at least 1 can be factored into n linear factors, and they're not necessarily distinct. In other words, if you have x minus 2 times x minus 2 times x minus 2, that counts as 3 factors, even though they're not distinct. They're not different from each other. And so the a sub n and the r's are complex numbers. So every complex polynomial function of degree at least 1 has exactly n complex zeros, some of which may repeat. So that idea of multiplicity will come in again. So here's one of the big keys to working with complex numbers, is the conjugate pairs theorem. So let's let f be a polynomial function whose coefficients are real numbers. So this is a subset. If the number r equals a plus bi is a zero of f, then the complex conjugate, r with the bar over it, that equals a minus bi, is also a zero of f. So in other words, if you have a polynomial function with real coefficients, the complex zeros occur in conjugate pairs. You'll never have 2i as a zero unless you also have negative 2i. You'll never have 1 plus 3i as a zero unless you also have 1 minus 3i. They always come in conjugate pairs. So if 3 plus 2i is a zero of a polynomial function, then 3 minus 2i is also a zero. If 4i is a zero, then negative 4i is also a zero. So that complex conjugate is, the sign is the opposite in front of the complex part. So let's look at this. This is switching now from zeros to factors. So remember, if r is a zero, then x minus r is a factor. So if 2 plus 5i is a 0, so this part is the 0. Now I have x minus the 0 as a factor, then x minus 2 minus 5i, the complex conjugate, is also a factor. So there's a corollary to this theorem. This is something that just kind of comes along practically for free, is any polynomial function with odd degree is going to have at least one 0. So it comes from this fact that the polynomial zeros that are complex come in pairs. And so if you have odd degree, then your degree can be written as 2k plus 1, where k is an integer. Does that make sense? So if I take 2k and k is 4, then I multiply it by 2, I get an even number. So then if I add 1, I get an odd number. So if the degree is odd, and all the complex conjugates come in pairs, there's always going to be one left over that will be the real 0. So if it's of odd degree, there'll always be at least one real 0. So suppose you're given that there's a polynomial of degree 6, and you're given some of its zeros. See if you can figure out what the other zeros are. So if I is a 0, then negative I is a 0. If 3 minus 2i is a 0, then 3 plus 2i is a 0. And if negative 2 plus I is a 0, then negative 2 minus I is a 0. And if I have a polynomial of degree 5 that has zeros 0, 1, 2, and I, well, we only get 5 zeros, and here's 1, 2, 3, 4 of them, so negative I is the 5th one, and that's all you get. Okay, so here's a different type of example that says make up your own polynomial function that has degree 4 and these zeros. So they tell you 2 of the zeros, so we can find additional zeros, negative I, and 1 minus 2i. So remember what we did before. If we said r is a 0, oh, that means x minus r is a factor. So we can build this polynomial by saying x minus I is a factor, x minus negative I is a factor, x minus 1 plus 2i is a factor, x minus 1 minus 2i is a factor. So my polynomial looks like multiply all that stuff together. Well, I'm going to show you some shortcuts. This is x minus I times x plus I. I'm going to simplify a little bit. X minus 1 minus 2i, x minus 1 plus 2i. So first I'm going to multiply these two together and get x squared plus ix minus ix minus I squared, which is plus 1. Okay, and then I'm still going to multiply by these other two guys. So I'm going to show you my box method. I do this x and minus 1 and minus 2i, and x and minus 1 and plus 2i. Then I make a box and multiply at the intersections of the rows and columns. So this is x squared minus x minus 2ix minus x plus 1 plus 2i, 2ix minus 2i minus 4i squared. So always you're going to get cancellation of the complex terms. Here's minus 2i and 2i. So it looks like I have x squared plus 1 times x squared minus 2x. Then minus 4i squared is minus 4 times negative 1. So that's 4. So this is plus 5. Okay, and then you need to multiply those polynomials together. So I would use a box again, because it just helps keep the terms a lot more organized. So I'd have x to the 4th minus 2x cubed, 5x squared, x squared minus 2x and 5. So I'd say my polynomial with those zeros is x to the